Dear students, now we are going to see the subject linear integrated circuit and the subject code is EC3451. Under that, the topic is basic operation of PLL and closed loop analysis of PLL. So basic operation of PLL and closed loop analysis of PLL. On completion of this topic, the students will be able to determine the closed loop analysis of PLL as well as the basic principle of operation of PLL. The basic PLL circuit that consists of three blocks. One is the phase detector, low pass filter and voltage controlled oscillator. The phase detector or the comparator compare the input frequency with the feedback frequency F out, and the PLL goes through three stages, that is the free running stage, capture stage and locked or tracking stage. Capture range, the range of frequency over which the PLL can occur a lock with an input signal is called the capture range. This parameter is also expressed as percentage of the phase detector output frequency F0, pull-in time, the total time taken by the PLL to establish a lock is called pull-in time. This depends on the initial phase and frequency difference between the two signals as well as the overall loop gain and loop filter characteristics. Lock-in range, once the PLL lock is locked, it can track the frequency changes in the incoming signal. The range of frequency over which the PLL can maintain a lock with the incoming signal is called lock-in range or a tracking range. So the closed loop analysis of PLL. So in the closed loop analysis of PLL, the first we are having a phase detector voltage to phase converter, and this one is applied to the summer. Then this output is applied to the K into V radiance amplifier, gain amplifier. Then it is applied to the applies to a system of transfer function f of s. This is applied to an error amplifier. This output is again fed to the voltage controlled oscillator. The voltage controlled oscillator output is again given to the voltage to phase converter. This one is this output is applied to the another input of the adder. So the input sinusoidal signal has a voltage gain Vi that is equal to Vp sine of omega t plus theta. So the phase shift of the signal at the voltage control oscillator output is theta. Then the average value of output of phase detector is V is equal to Kd into theta I minus theta oscillation. So here the theta I and theta oscillation represent the phase shift. The phase of the signal at the output of voltage controlled oscillator is a function of time and is equal to the integral of voltage controlled oscillator output frequency. This can be expressed as omega of oscillation of t is equal to d theta of oscillation as a function of t divided by dt. So now cross multiply this dt of oscillation t equal to omega oscillation of t into dt. Now we integrate both sides. So dt of integration of dt of oscillation of t equal to integration of omega oscillation of t into dt plus theta oscillation at t is equal to 0. So integration and differentiation get cancelled. So the theta oscillation of t equal to integration of omega oscillation of t into dt plus theta oscillation at t is equal to 0. The integral component is represented as 1 by s inside the voltage controlled oscillator block, and the oscillator frequency omega oscillation and the DC voltage Vc are related by omega oscillation equal to omega c plus k naught into Vc. The omega c is the center or the free running angular frequency. Vc equal to 0 and k naught is the VCO gain in radian per second per volt. The closed loop transfer function of PLL is Vc of s divided by theta I of s, that is equal to Kd into f of s into a divided by 1 plus Kd a into f of s into k naught by s. Simplify this. So s Kd f of s a divided by s plus Kd a f of s into k naught. So the response loop to the frequency variation of the input and then phases Vc of s divided by omega I of s is equal to Vc of s divided by s into theta I of s, that is equal to kd f of s into a divided by s plus kd a into f of s into k naught. Omega 1 is equal to d theta I by dt and omega I of s is equal to s into theta I of s. F of s is 0 with the loop having a first order low frequency response. So the ratio of voltage to angular frequency is kV by s plus kV into 1 by k naught. So this can be written as kV represent the loop bandwidth, kV is equal to k naught into kd into a. Second order phase lock loop. The first order loop without loop filter has several limitations. Both the sum and different frequency component are fed to the output from the phase detector. All out-of band interfering signal from the input will appear shifted in frequency at the output. The most common configuration of monolithic PLL in second order loop with the loop filter F of S of a simple single pole low pass filter realized with a resistor R and a capacitor C in figure. So f of is equal to 1 by SC divided by R plus 1 by SC, that is equal to 1 divided by 1 plus SRC. So RC is replaced, 1 by RC is replaced by omega. So 1 divided by 1 plus S by omega, 1 divided by 1 plus S into tau. So tau is equal to 1 by RC, that is equal to omega. 1 by omega. Resulting block diagram of second order PLL using a single pole loop filter is shown in figure. So the input has a summer, the feedback path has a voltage control signal K0 Js, and the forward path has a gain factor Kd and the transfer function f of s, then is applied to the amplifier of gain A. Loop lock range and capture range. The loop lock range is represented as the range of frequency about omega naught for which the PLL maintains a relationship between omega I equal to omega oscillation. The phase detector can also determine the phase difference between theta I is equal to theta oscillation over a plus or minus pi by 2 range. Then the lock-in range is defined as omega L is equal to plus or minus theta omega oscillation, that is equal to kd a k naught plus or minus pi by 2, that is equal to plus or minus kv pi by 2. The capture range is the range of input frequency within which initially unlocked loop will get locked with the input signal. When f of s is equal to 1, the capture range equals the lock-in range. F of s is equal to 1 divided by 1 plus s by omega I. The capture range is smaller than the lock range. There are some possible questions. The output voltage of phase detector is the phase detector compare the input frequency with the feedback frequency and produces output DC voltage called error voltage. What is the function of low pass filter in phase lock loop? The low pass filter removes the high frequency noise and produces a DC level. Thank you.